Okay, Assalamualaikum and a good afternoon or morning, wherever you are. Okay, welcome to the public lecture, which is done in conjunction with the World Quantum Day. We have already been doing a few days with our event EQuaLS 2022, and we are sort of closing the event with this public lecture. So we are fortunate to have Professor Bob Coecke to be delivering this public lecture. Let me introduce Professor Bob Coecke. He obtained his doctorate in sciences at Universiti Brussels. I hope I've pronounced that right. And did a postdoc in Theoretical Physics Group of Imperial College, London, and also in Category Theory Group of the Maths and Statistics Department at McGill University in Montreal, and also Department of Pure Maths and Mathematical Statistics of Cambridge University, and finally settling down in Department of Computer Science, University of Oxford. So he was a professor of quantum foundations, logics and structures at Oxford University since 2011 until 2020, and currently is now the chief scientist of Cambridge Quantum Computing. He's a pioneer of categorical quantum mechanics, quantum pictorialism, ZX calculus, disco-cat model for natural language, and quantum natural language processing. He's a founding father of the quantum physics and logic community and conference series, and also of the applied category theory community, and also part of the editor of the open access journal Compositionality. I think probably it's over you, Bob. Bob, are you there?
Yes, I'm here. Yeah. Oh, sorry.
So so I finished reading your.
Okay. Thank you.
Yeah. Welcome.
Okay, thank you, Islam. I actually have been. I'm now not physically in Malaysia, but actually I've been there twice before. Can't remember, maybe in 2007, 2008, and 2013 or 14, I think. So it's good to be back, although this time virtually. And so what I'm going to talk about today is quantum AI from high school quantum pictures. As this is a public lecture, I've tried to tone down as much as possible the technicalities so that it's more broadly accessible. So basically the idea here is that for many years now, and this will be of course explained in many details, I've actually been driven by something which is a new formalism for quantum mechanics, which is supposed to be much more broadly accessible than the current formalism of quantum mechanics. And as a major bonus, well, it's actually more than a major bonus, is that actually this same formalism is now generating new quantum technologies as we speak. So it's the interesting case that making something simpler actually also produces new technology. And I'm in the fortunate position that by leaving academia, well, not fully, of course, but I'm still mostly an academic in thinking and activity. But in any way, by leaving academics, I got the opportunity to actually develop that technology myself, following from the research I did before. So let me tell a little bit more about myself. So I'm going to share screen now. Up. So like Isham said, I used to be a professor at Oxford University. I was there for about 20 years, and my leaving date is not that far ago. It was like first 1st of January 2021. While at Oxford, we built a very big group there. This was an interdisciplinary group with people from backgrounds in computer science, in physics, in mathematics, some philosophy, some cognitive science and psychology. I'm probably missing some here, some backgrounds, but so it was quite a varied group. I'm just looking at the people here. Yeah, some were even doing economics and stuff like that. So it was quite a varied group with a lot of different backgrounds. So I basically left my faculty position there, and a lot of these people actually came with me. A lot of these people, and some who were there in the past time and those who were faculty position, came back to me. So initially I became chief scientist at what then was called Cambridge Quantum, which is a quantum computing company initially founded in Cambridge by Elias Khan, but which meanwhile has spread out, well, with a lot of people in London, people in Tokyo, people in Oxford now, new German offices has been opened. There's some people in the US too. So it became like quite an international company. And then even more recent, it wasn't Cambridge Quantum anymore. Now I'm talking very recent. It became Quantinuum. So Quantinuum was the result of a merger of what used to be part of Honeywell Quantum Systems. I mean, if you know Honeywell Quantum Solutions. So if you look to your heating system, you probably see Honeywell up there, or there's many other control systems where you will see the name Honeywell. So Honeywell had a quantum development facility. So the quantum development facility split off from Honeywell, and then we merged them together. So they actually have a quantum computer. So now we actually have our own quantum computer. But so Honeywell, the big company, is still like a main investor in us, and so is IBM. So we also work with IBM quantum computers, and we're also working with other quantum computing companies. So we're a little bit agnostic about the hardware, which is kind of essential for a company which does a lot of software. Anyway, so that's where I am now. So besides my global role as chief scientist, I've also over the past year and a half built my own team based at Oxford. And the topic of what I'm going to talk about is the main focus of what we do with my team in Oxford, especially the sort of development of quantum natural language processing and quantum AI more broadly. But we also focus on, in my team, on this educational aspect I will mention today, and things like the further development of ZX calculus and diagrammatic meaning more generally. So a lot of the people in my team either moved immediately with me from the Oxford team, or went somewhere else for many years and then came back. For example, Steve Clark, who top second from the left. He used to be faculty in Oxford, then he became faculty in Cambridge, then he went to DeepMind, and now he's back working. And you'll see later in the talk that he did fundamental work in the 2007, 2008, about the things we are now doing. So people actually rejoined, which was a very nice thing to happen. Okay, let's start now with the actual content. So, and I'm going to talk about the language of quantum. What is the language of quantum? This is what scientists would use to talk about quantum. So typically it's conceived as mathematics, of course. It's what kind of mathematical language would you use to talk about quantum? And it's not just about mathematics usually. There is like a layer on top of the mathematics which connects the mathematics with things in the real world. So it's not that any scientific theory is ever purely mathematics. Scientific theory is a piece of mathematics typically, and its relationship to the real world in which we operate. And so I'm going to talk about a few people in this context about the language for quantum. On the left, you see John von Neumann. I'll talk about them individually. In the middle, you see Erwin Schrödinger. And on the right, you see Roger Penrose. Two of them got Nobel Prizes, Schrödinger and Penrose. Schrödinger got a Nobel Prize for quantum-related stuff. I mean, you may remember his equation, like the equation people use for evolving systems in quantum systems, like what happens to quantum systems when you let them do their thing. And The third one, Roger Penrose, got his Nobel Prize only very recently, but this was actually for black hole physics, not for quantum. This was for black hole physics. And the one on the left didn't get a Nobel Prize, and the reason is that he was mostly a mathematician, and there is no Nobel Prize for mathematics. But that said, is probably, if not the biggest mathematician of the previous century, undoubtedly, and he did a lot more than mathematics. So they're really three superstars from the previous century, and just to place them. So let's start with John von Neumann. So John von Neumann is somebody who, I mean, who probably should have gotten a Nobel Prize economics, because he kind of invented game theory and things like that. I don't know why he didn't, probably because at the time game theory wasn't identified yet with economy, and now so much of economy depends on game theory. He also invented so many things in pure mathematics, and in physics. What he did is actually he came up with the language of quantum as we use it. We have been using it till now. So language of quantum, as the scientists have been using till now, was a result of John von Neumann, which he published in his book around 1930. The book is still, if you take the book now and you want to study quantum, it's pretty total. It's still completely accurate for like the mainstream language which people have used. Now, a very interesting thing about von Neumann, and there aren't many scientists who have that sort of bravery, is, and you have to only look at the first two sentences here. It isn't correct English, but it doesn't matter. I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. So now to translate this in simple language, Hilbert space is what von Neumann proposed as the language of quantum. So that von Neumann said, okay, for quantum we need to use Hilbert space. He proposes in his book, like I mentioned, like around 1930, and then in 1935 he basically denounced his own proposal to use Hilbert space of the language for quantum. I mean, we're almost 100 years later now, a bit over 90, and most people are still using that language as the language for quantum, exactly as he proposed. On the other hand, von Neumann, one of the smartest, if not the smartest mathematician of the previous century, he went on to try to look for different languages, alternative languages. He invented new mathematics as possible alternative languages for quantum. But it never, I mean, none of them never really kicked in the sense that they weren't really successful. One measure of success is that nobody's really using them anymore for the sake of quantum. I should say for the sake of quantum, because all that stuff is actually used for many other things, which he invented, these mathematics. But there is also a conceptual which interpretation of the languages he proposed, why these weren't probably appropriate languages for quantum with what we understand now about quantum. I mean, this would be a different seminar, a philosophical one. I'm not going to go into that. I want to present constructive things rather than criticism of a previous attempt. So I'm not going to go into that, but I'm happy to discuss this offline or on one of the forums I am, like on Twitter. So anyway, so this was von Neumann's contribution. He said, maybe we should look further than the Hilbert space, which is the mostly used model of quantum as a quantum language. Maybe we should look further to that. So something else von Neumann did was, and that's which guided his possible alternatives to Hilbert space. He felt that quantum measurement was the most important thing of quantum. Now, what is quantum measurement? Quantum measurement is what happens when you observe a quantum system. So when you observe a quantum system, it won't be the same as me just looking at the screen. So if I look at the screen, I see what's there and I read what's there. Like a quantum measurement doesn't work like that. If you got a quantum system that is in a certain state, which is like in a certain state of being, say, and you observe it, that's not really what you're going to see necessarily. You may see something else, and you may actually even alter that state of being. And then von Neumann felt that, yeah, that's really the most important thing about quantum mechanics, this change in what we consider as looking at something. this change in what we consider as observing something. And a lot of his work in trying to change the language of quantum was driven by that. So he started this in 1935, and interestingly enough, in 1935, Erwin Schrödinger had a different view than von Neumann. He said, well, maybe it's not just about this observation, maybe it's about something else. And his focus was really thinking about what happens if you put two quantum systems together. If you put two systems together here, like me holding two pens, I mean, if I bring them together from far and I bring them together, they still are two separate pens. Like this pen leads an existence independent of this pen. They're just two separate pens. Now, what happens with quantum systems, if I would put them together and let them interact, they become one whole. They become one whole. They stop being like two individual pens. And Schrödinger believed that this was actually more characteristic about quantum than the way we observe it. So this was a completely different position which Schrödinger held. And this went somewhat unnoticed at the time. This went somewhat unnoticed. Nobody really, so von Neumann himself followed up on his beliefs. Schrödinger didn't follow up on his beliefs too much. And the reason now in hindsight, I would claim, is that the right mathematics wasn't available to properly do that. So we didn't have the right mathematics yet to actually follow up on Schrödinger's idea. And so really there is this, so really remember, it's all about if you put multiple things together. Now, another reason why it may not have been picked up is because very much so, for a long time already, science is about looking inside a system. Like if you would ask yourself, what is this pen about? Then you would open the pen and you would see that there is ink inside and that it can go outside to the front. So by the ink coming outside, you can use it to write. So that's been mostly the focus, like of science. So for a human, like it would be like how do we become who we are? Well, look at our genes and see how our genes produce who we are. So that's one calls this reductionist thinking. So science was very much dictated by a reductionist thinking. A reductionist thinking is about looking inside something, what it is made up from. And in physics, like, okay, what is this particle made up from? Oh, smaller particles. And what is small particle made up? Oh, small particles. So it's sort of a way to look at things by looking at the inside. Now, there are other ways to look at things. For example, if you meet somebody and you need to do something together, or you want to become friends or something like that, you're not particularly interested in what's inside that person. You're not particularly interested in which organs this person has or things like that. You're interested in how this person will treat you, how this person will interact with you, which is a very different thing. So it's about you and that person, how you would interact together, how you could live together, whatever, how you could do things together. So it's about two things, about yourself and the other person. And that's kind of a perspective which was pushed forward by Schrödinger. It's about how things interact with each other when you bring them together, rather than what's inside somebody and how one looks inside of somebody. They aren't independent. If you think about humans, they aren't independent, because when you interact, you also try to understand a little bit what's inside the person's head. But so they aren't interacted. But it was an important question to say, what are we going to think as the most basic words for the language of quantum? And so Schrödinger's view is it's about how multiple things interact. Okay. Now and basically he put this idea forward in this paper about like it says the probability relations between separated systems. So you've got two quantum systems and what happens if you bring them together. So from 1935. So the third person I'm going to bring forward would not be associated with the development of quantum at all. It wouldn't be associated at all with development of quantum, while maybe in the popular domain, Hawking is a little bit more popular than Penrose. But so the sort of things which Hawking is popular about, a lot of it was actually invented by Penrose. So it was the mathematics of black holes, for which he got the Nobel Prize a bit over a year ago. Penrose is actually also based in Oxford, like ourselves, and still active there. So he got this Nobel Prize specifically for his work on black holes. But Penrose also did other things. He did many other things. Maybe you remember him from weird things like this, like staircases where you keep on walking up and down, and on the mathematical understanding of weird things like that. This is called Penrose Staircase. Penrose was a good friend of Escher. So a lot of the Escher's painting were the result of interactions of Escher with Penrose. But that's not what I'm going to talk about here. What I'm going to talk about here is something else. So in some of Penrose's work, you will find these sort of things. And this goes back to the 1970s. And what you see on the left-hand side mathematical symbols you see the squiggly arrows. On the left-hand side, you see symbols, like on left top, you see Q with then A, B, C, and F, G. And on the right-hand side, you see a picture. And you see a few incarnations of something on the left that becomes a picture on the right-hand side. So what Penrose came up with, and this was in the specific case of what's called relativity, general relativity theory, where black holes and things like that are studied. So he found the easier way to represent the mathematics of general relativity theory using pictures. And he actually did this while he was still an undergraduate study, because he was studying this stuff at school, and he felt that there were better representation. There was better language for relativity than the ones usually used, or at least a more intuitive one easier to work with. So, and this will be a major contribution to what I will be talking about today, although at the time, it wasn't at all intended initially to have anything to do with quantum. Initially. Okay, so basically now we do fast forward from long ago. The starting point of my work relevant to what I'm talking about was something, a paper in 2004 with Samson Abramsky. It was called the Categorical Semantics of Quantum Protocol. And I mean, this is the paper which made my personal career. It's for this paper I got like faculty position. I became a professor at Oxford. And so if you think about it, it was trying to realize Schrödinger's dream, which is to actually have a language of quantum, which is all about putting systems together and how they interact as the first-class citizen, like a language of quantum, which mostly focuses on bringing systems together as a third-class citizen. And we used to realize that Penrose's pictures. We used Penrose's picture as a language to start, in order to start a new language for quantum, which was mostly about bringing things together. Now, I say sort of because if you look in this paper, you actually don't find many pictures in there. There aren't many pictures in this paper, although I say this is actually Schrödinger's dream via Penrose's picture. So while we used Penrose's language, we kind of used a modern version of the same language, picture language of Penrose, but which actually doesn't really have that many pictures in it. It's called category theory. So you see this in the title, Categorical Semantics of Quantum Protocols. So we used category theory, but we used category theory which was equivalent, which was the same as Penrose's pictures. Now I'm going to talk a little bit sociology. I'm going to give a sociological rant here. There is something really weird about science and academia. And what's weird about science and academia is that if something doesn't look complicated, people don't take it serious. It's a disease. It's really an illness which lives within scientists and academics, that if it doesn't look difficult, it's not taken seriously. So probably if you would have used Penrose's pictures in the same paper, it would have been rejected. It would not have taken seriously because people would say, oh, pictures, like something complicated and quantum can never be formulated in pictures. That would have been the reaction. We would have been branded not serious scientists. This paper would never have properly existed and known about, and I would never have a scientific career. That's how simple it is. And so we actually wrote this down in the language which was expected by the sort of conferences and journals where we published it. And that was the difficult language of category theory. I mean, it's important to understand that other language is kind of the same. But okay, so we published that. And that's why there aren't actually many pictures in that, although it was really Schrödinger's dream via Penrose's pictures. So now, Now, I became a bit braver. Because I mean, I've been always, because I was actually writing on my own. So I wrote another paper like a year later, which was very much the same story, but you can immediately see from the title that I didn't care anymore about being taken seriously or not, but those people who expect things to look complicated. So I made a statement. I published this paper with a title, Kindergarten Quantum Mechanics. And this was really about Schrödinger's dream via Penrose's pictures. However, this was just a start. This was just a start. This was just a start of trying to do that, trying to change the language of quantum to a language of pictures. What we did in this paper and the previous one was actually only a very small part of quantum. We did only a very small part of quantum, but we did enough to show that there was a roadmap there, that there was a possible plan to try to get all of quantum mechanics in pictures like Penrose's, but we had to invent new kind of pictures. Penrose's pictures were really not enough for getting all of quantum. We need to go beyond Penrose's pictures to really get all the way to quantum. But okay, the plan was set. The direction was clear by using the word kindergarten. By the way, if you read this, don't expect that your child from kindergarten can understand this paper. No way, no way. This isn't an easy paper. It just has the provocative title of saying, this is where we're trying to go. And we're not even there yet now. But we're getting close now. So instead of the usual equations you would find in a quantum paper, in that paper you find picture like this. I'll explain later what this picture means. So it introduces a new language which looks like pictures. I'm not going to elaborate on this one now okay. We're now 13 years later, and in the shops you can find this book. It's called Picturing Quantum Processes, and this is basically the plan I was just talking about realized. So we worked really hard with many people, and by say 2013, 2014, we felt we had done so much of quantum with the picture language that we could actually teach an entire course of quantum just using picture language. And that's what we actually started to do at Oxford University. We started from then on to teach quantum just with picture language. And gradually then that course, or what we taught in that course, this was me and Alex Kissinger, became this book, which is now referred to as the Dodo book because there's a dodo on the cover. So yes, okay. So this was 2017. So the plan succeeded, so to say. The plan to come up with a new language for quantum based on pictures succeeded. Now fast forward, and okay, so the sort of things which you see in there, the kind of mathematics, is really about, you take a piece of wire and you stretch it, you yank it. So you take any piece of wire like here and you yank it. This is the sort of mathematics. This is how you reason mathematically in these things. It's like you work with wires which you yank, and then you've got other mechanisms you see. Think of this wire on the left as having some bead on it, like there is this box which I give a real shape. And it's not hard to imagine that if I pull hard on these two side wires, that this box is going to turn around. So this is sort of new maths we used, new mathematics we used to formulate quantum mechanics. And I'll explain more about this later explicitly. Now, this is an interesting picture because this is Schrödinger's grandson. This is Schrödinger's grandson now, not Schrödinger anymore, who's feeding my daughter, and is feeding her wires. He's feeding spaghetti wires. So he's actually teaching her quantum in a way. This is a picture from a few years ago. So actually Schrödinger's grandson, this person is called Terry Rudolph, and Terry Rudolph is now also the head scientist of an important quantum company, one of the very big ones like Quantinuum. It's called PsiQuantum, and they're based in the US, in California. And so Terry is the head scientist now. And actually we're working together now, which is kind of nice, given the history which I told you about. Actually, Terry had been known of our work and has been interested of our work from the first paper, which I said, the difficult one. He's been interested there, and he invited us over to give like a 4-hour seminar at Imperial College about it. I remember in 2004, a long time ago. So we're in contact a long time ago. Okay, fast forward again, 5 years later. Okay, so there have been some headlines of work we've been doing recently, and in all over the media, and also in places like Forbes, and say Cambridge Quantum makes quantum natural language processing a reality. So what's natural language processing? Natural language processing is is basically to some extent what we're doing now. It's anywhere where you interact with a computer with language. Like, for example, when you do a Google search, you do a translation, you use Siri or something like that. That's natural language processing. And so we started a field called quantum natural language processing, which is fundamentally different than the way or the engineering behind the natural language processing which you're using every day. So we started that, and it's entirely based on the quantum picture language. Without a quantum picture language, this field would not exist at all. So this new idea on this new quantum language actually has meanwhile generated new kinds of technologies. And only 2 days ago, we put out a new version. So you see the change from Cambridge Quantum to Quantinuum here in the headlines. So yeah, so my team is working on that, and I'll explain more about this later. So, okay, I'm gonna. So I mean, I've talked about like a simple language for quantum pictures, and this is all about inclusivity. This is all about inclusivity. This is all about making things accessible for people. Now, this book, which is called the Dodo book, which we use to teach quantum, it isn't really for everybody. You really need to be at university to be able to read it. If you're not at university, you can't read that book. And therefore, we actually wanted quantum, because we wanted to make quantum simple against the sort of doctrine of scientists and scientific communities. So what we did is we just had to write another book which is readable for everybody. That's what we had to do. And that's meanwhile more or less done. It should be coming out in 2-3 months. So unfortunately, it's not ready. And now, I mean, I'm not going to go through this page. I'll explain some things about it, but you probably immediately see that it's much more friendly to a younger audience than any standard mathematics book would be. So I'll explain some of the things inside this page later, but the main idea is that it's really a book that should be accessible at the very least at high school level. Not yet kindergarten, but at the very least at high school level. So that's where now. So that's where we gotten. So the book will come out in 2-3 months. And it's non-trivial. I mean, you'll see stuff in there. I mean, I'm not going to explain this at all today, but in that book, which is, it's like about, at the moment, like 150 pages like this. So these are pages with not much on it, not much text on it, just a bunch of pictures. But in these 150 pages, you'll be learning state-of-the-art techniques, which didn't exist 2-3 years ago, for quantum technology, state-of-the-art techniques for quantum technology, which are about how to make your quantum computer work at its best and things like that, which in technical terms is quantum compiler optimization. So really new techniques you'll find in that book, as well as some of the most foundational things in quantum mechanics, like showing that quantum mechanics is non-local. So this is the sort of spooky action type thing people talk about in quantum mechanics, the spooky action at a distance type thing. We show these things also in our book. So we really go very far in what's considered as sophisticated quantum using this picture language. Besides the book, we're also my office. This is not my office. I'm at home now. This is my home. This was my home office during COVID, and it's also my music studio. But we're now at my other office, like at Quantinuum, which is also in Oxford, my office. We're now filming also. We're filming lectures of the book. So because people might rather like watch lectures than actually reading the book. And so we're also filming the lectures. And who you see here being filmed is Stefano Goggioso, who's the co-author of the book and who did most of the nice pictures, I should say. So he's a much better drawer than I am. So Stefano is also a former PhD student of me. Alex Kissinger, who I wrote the other book with, is also a former PhD student of me. And both of them are now faculty at Oxford. And in the group I've built at Oxford. So they kind of took over from me. So I'm now granddad. So it's like two of my children took over the group and I'm granddad. So I really didn't want to stay there anymore because it would really make me feel very old. So, okay. So Stefano and Alex are now running the show there, also together with John Barrett. Okay. So, and another thing we are doing, so we're doing a book, we're doing the lectures, and we're also doing an experiment. And we're doing the experiment, and this is teaching teenagers with the book and the lectures we are filming, what's inside the book. And then we're going to make them do an exam. We're going to make them do an exam, make them do some exercises. And then we're going to also take some Oxford students and make them do some exercises. We'll also take some Oxford students, make them do some exercises, the same exercise, but the Oxford student have got a normal quantum course, a regular quantum course, actually a course by John Barrett, who I just mentioned, is also in my group, but they get the same questions. And we're going to show that the high school children will do at least as well on some of the questions as the Oxford students will do. So that's the proof of concept that this really is going to make a big difference. So that's also ongoing. And they all go hand in hand, of course. We needed the book to do the experiment. We needed the lectures to do the experiment. So now we're actually doing the experiment. And something else I'm afraid to say is we've been trying to do this experiment for years within academia. It was impossible. It was just impossible. We didn't get any support from the university or anything like that. Nobody supported us. Now that we're actually in the private sector, this is so easy. We get so much support for this. Also IBM is helping us now. So this is really just possible because it's a very academic thing, but it only really became possible by me leaving academia, which is a little bit of a shame. While we're doing it in collaboration with Oxford University, both Stefano and Alex are of course involved in this, and John with his course. So as a collaboration with academia, it's now the best possible way to do this. Because it's very hard to get like the financial resources for this in an academic context, because again, it's not about showing something difficult. It's about making something look easy, and it's so hard to find money for that. Okay, I'm now going to go a little bit through a small part of this new book and teaching you how things go there and the sort of stuff we teach there. So basically, this I'm going very fast, by the way. This would take a much longer time if you teach this properly, but I just want to give you a feel on how things are. So basically, what we're talking about in the book is about particles traveling through wires and boxes. So it's all about wires and boxes. For example, here you got a battery and you got a lamp. You have to think of the battery and the lamp as boxes, and then you got an electrical wire in between. This is your wire. And then there are particles traveling in this wire, which are basically electricity particles. That's how we are taught that. They're electricity particles traveling to the wire, which go from one box, which is the battery, to another box, which is the light bulb. And of course, then the light bulb shines. So this is the idea of particles and boxes. I mean, here is another idea of particles and boxes. Like you got a pump, you pump up wire, it produces wire. Then you got a wire, a water, I say, then you got a wire, where the water particles now travel to, and then you can use them to actually spread the water particles on the flowers, and then the flower is going to take in the water particles, and that's going to make the flowers grow. So the flowers are also like a box here. So you got wires and boxes. Here is a more complicated system of wires and boxes. You got your laptop and maybe your router and your another screen and a computer somewhere else and a printer and a recorder. This is a much more complicated system of wires and boxes. So you see clearly what the boxes are: your laptop, your TV, your router, your screen. So we're going to now make a language of wires and boxes, and we're going to then later say, okay, let's take this as a language for quantum, a language of wires and boxes. Right. So okay, now. Just to make things simple, a wire is just a wire, you draw it as a wire, and a box is just a box. You draw it as a box, and then to distinguish different boxes, we may put a label on the box. Here we put a little heart. This is in order to distinguish different boxes. You may see I took like some sort of weird shape for the box, not just a rectangle or a square. And the reason will become clear later. It's when we rotate when we turn the box upside down, we want to be able to see that it's actually turned upside down. That's the reason. So that if we move the box and we start rotating it, that we actually see that it's rotated. That's why we don't take a regular rectangle. But that's not so important. So if you think of such a box, we think of an input wire, something where particles go in at the bottom and something where particles go out at the top. So that's basically how we're going to think of the wire and the boxes. Right. Okay. There will be some special box. Remember the light bulb and the battery. Like the battery and no wires coming in. It's like the battery gives electricity to the light bulb. The battery gives electricity to the light bulb. So you can think of a battery as something with no output, and as the light bulb as something with no input. So the electricity goes from the battery to the light bulb. And so there are boxes with no input and no output, and we can give them names. The ones with no input we call states, and this is because this is how scientists call these things in physics and in computer science and stuff like that. And we will call the one with no output a test. I mean, you could come up with different names, but we decided to go for test for reasons I'm not going to explain today, but there are people who know quantum will know that there are good reasons to call them test. So we got boxes with no input and no output, and then we can put all these boxes together, and they then form a diagram. They form a diagram. A diagram is basically take a bunch of boxes, they can be different boxes, and plug them together. I mean, it may be the case that some of, I mean, I've drawn all the wires the same, but they don't really have to be the same. It could be that some of these wires are electricity wires, and some of these wires are actually water. I mean, if you've got an electrical pump, then you'll need electricity to start the pump, and the pump will produce water. And you have to be very careful to distinguish the water from the electricity, because you don't want to start pouring water on your electrical device. That's not going to be good. You don't want to start pouring water on your computer neither. So because then of course it's going to break. So it's very important to know which wires are what. I mean, we should have put names here, and we could have put names here, but okay, we'll see later that we'll draw different wires in different ways. Okay, now you can draw the same, we call these things diagrams. You can draw the same diagrams in many different ways. What you see here on the left is like we have a green wire going into a heart and a red wire coming out. If you look to the right, we still have a green wire going into a heart and a red wire coming out, despite the fact that the boxes have been moved around a bit. So an important thing of these pictures is it doesn't really matter if you move boxes around. It doesn't really matter. The important thing is how these boxes are connected together. And if you want to be, and the picture on the right looks a little bit more complicated. So it's probably easier to work with the picture on the left. There's no reason to actually start swapping these wires around. You know, it's the same thing. When I play music and I got a lot of these cables here, like guitar cables and lots of cables. And then you want to keep your cables apart, because if they start being knotted together, you don't know anymore which cable is going where. You don't know this anymore. And then things become complicated. So you want to keep your cables clean and tidy, because it makes it easier to work with. Okay, let's continue. So basically, if we got something, so I mean, sometimes we write like 1 + 1 = 2, 1 + 1 = 2. And similarly here, you can stick an equal sign between two diagrams. Because we said these two things are the same from the previous picture, to say that they are the same, we stick an equal sign in the middle. Just like you say 1 + 1 = 2. It's the same. I mean, we're not talking about numbers here, but it's the same idea. You just say they are actually the same picture. It doesn't, because we just moved some boxes around while keeping the wires. Okay, now we're going to start talking. So I'm saying, like, if you read this in our book, it goes much slower. So I'm actually going really fast here, just because I just want to give you the idea of these things. So, okay, now here is an example of a wire on two sides of the equation, which is kind of the same wire. The only difference, and I'm going to use one of my guitar cables here to demonstrate this. Okay, I'm going to take this guitar cable here. Whoop. So you have to look at my screen now. I mean, it's a bit long. It's a bit long, but you see, this is the same. What I'm holding here is the same shape as the picture on the left, right? It's the same shape as the picture on the left. You see, you have to look at my screen now. So whoop, what I do now is, whoop, I straighten it. That's all. Whoop, I straighten it. That's all I'm doing. It's still the same wire. It's still equally useful to play guitar if I hold it like that or I hold it like that, because it's just the same thing, right? It's just the same thing. So this is the same wire. So we consider them as equal. And that's why you see here, they got, so I'm going back to the screen now. You see this, this like snaky wire being equal to the other ones. Now, so that this is obvious, this is obviously twice the same diagram. There's no boxes here initially. It doesn't look as if there is boxes, but I mean, there is no reason. What you can do actually is to, as you see here, to take this cap shape, you see this cap shape thing at the top, and think of it as a box. Why not? It's a box with 2 inputs and no outputs. So it's what we call the test. It has 2 inputs and no outputs. So we can think of it as a box. And you can also think of the cup-shaped wire as a box, and that's a state. That's a state. And for people who know physics or some quantum, this is what you should think of as something like a Bell state or an EPR state, the one at the bottom. So just to start to make you see, for those who already know quantum language, the usual, how this is starting to get connected to things you know. So this is called a Bell state or an EPR state or an entangled state, but we just represent this as a piece of cup-shaped wire. And that's where the power is going to come, that a lot of standard notions in quantum will be representable just as pieces of wires and things like that. Everything pretty much as pieces of wires. Everything will be represented as pieces of wire, and all the mathematics is just thinking about what you can do with wires. That's really what this is all about. This is really what this is all about. So we call this cup and cap, but if you want to, you can call the cup the Bell state or the EPR state or an entangled state or whatever language you want, word from standard quantum you want to use. Okay, now what's funny about like cups is you can sort of slide boxes around it. And that's going to be becoming very powerful in sort of doing useful things with this. So if you got a box like the one on the left, then you can slide it around. And now you see why we actually made this weird shape, took these weird shapes, because you want to see that the box on the right has been slided around this piece of wire in the process, right? So that's what you can do. And then I kind of showed the picture like that before too. If you have a diagram like the left, like you got this box, a piece of wire comes out of the top and you bend it down, and a piece of wire comes out of the bottom and you bend it up, then you pull hard, then it will make the box rotate. I mean, I had a picture like that before. So it will make the box rotate. So that's the sort of things. And this is the kind of mathematics you're doing now. And this is actually a lot more powerful than you will imagine. Okay. Now, usually when you think of quantum systems and stuff like that, like for example, also like our pump and our water hose and our battery and our light, then the light switch will be somewhere on the wall, and the light will be somewhere else. The light switch will not necessarily be exactly on the light, and then the pump will be somewhere, and your flower will be somewhere else. So how do we think about here and there or somewhere else in these terms of pictures? Well, if you look at the bottom of the picture, we got like one box which is school, another box which is office. Obviously, the school and the office are in different places. So if we put 2 boxes side by side, then we will want to typically think of them as being in different places. We want to think of them as being in different places. So that's where space comes in, like being in different places. I mean, so 2 boxes side by side, think of them as being in different places. We'll say where they are. You can draw, you'll see an example in the next slide, that we actually say, okay, this box is here and that box is there. So they're in different places like school But then of course we can use wires to make the children and parents go from the different places and get them in the same place, like home. They both go home, kids after school, parents after work, they go home, and home is then another box where things happen. So now you see that you heard me say after school and after work we go home. So you can think of the picture on top. You can think of the picture on top as happening later than the picture at the bottom. First you go to school, first you go to office, and then you go home. Then you go home. So that's really what these pictures are about. So space and time. So we got space as different as being apart, and time as something happening later. So above is later, before, below is before, and that's how you want to think. Okay, here is an example. So what you see here is you see one of these cup-shaped wires. You see one of these cup-shaped wires at the bottom, right? At the bottom of the screen, you see one of these cup-shaped wires, and then you see two wires coming out, and the thing in the middle is supposed to be a galaxy. It may not look like a galaxy, but okay. So it's supposed to be a galaxy. So you start with like this thing, say wherever we are on Earth in the middle of the galaxy, or wherever we are in the galaxy. So we've got this cup-shaped wire. We've got two things coming out. So think of it as two particles coming out. One goes to one side of the galaxy where Andrea is. We say Andrea is on one side of the galaxies. And then one goes to the other side of the galaxy, and there is a person called Blaise. So now Andrea and Blaise each have a box, and there's a particle coming from wherever somebody else is on Earth, and one is sent to Andrea and one is sent to Blaise. And then they can use a box to do something to the particle. That's the way to think about this picture. And it's of course, I mean, it's of course important. It will be very important that these two particles were sent from the same place out of this special cup. I mean, you will see how this sort of thing works. And basically this idea, this simple idea in this picture, that something that you've got this cup state in the middle, and you send things to the left and you send things to the right, is really, really studied a lot in quantum. It studies so much this particular situation, typically not with a galaxy inside, but like two sides of the laboratory or something like that. This has been studied intensely since the 1970s and the 1980s, and so many physicists are mainly doing exactly this. Again, not two sides of a galaxy, but people are starting to do things like between satellites now. So there's a lot of stuff people are working on. Okay, now I'm going to show you something that's very important quantum thing, and that's called quantum teleportation. Quantum teleportation. So here we got our galaxy. Here we got our galaxy. Think of the left-hand side as the same picture of before, but we take away the two boxes. We take away the boxes, and instead we start with one box here, also on the left-hand side, and then we put this cap thing. So we got this thing in the middle, we got this cup thing in the middle. One is sent to one side of the galaxy, the other one is sent to the other side of the galaxy. This was Andrea's side, and then Andrea has another box here, a state, and then puts one of these cap wires here. She puts one of these cap wires here. So Andrea is doing some stuff on the left-hand side. You think of Blaise's situation is the same, although he doesn't have a box. And now, if you follow our idea about that we can actually slide things along wires, you can actually slide this box now up and up and up, up and up along this wire. You can move this box along the wire because it doesn't change anything, all the way there, all the way there, all the way there. And so on the right-hand side, you see the box ending up there. This is sort of the basic principle behind quantum teleportation. This is sort of the basic principle behind something called quantum teleportation. You can move this box. You can move this box from one side using this thing to the other side. That's called quantum teleportation. And this is really when I talked about the papers in 2004 or 2005, where I said we use Penrose's language to do something about Schrödinger's dream. This is really what you would find in these papers, this way of thinking about teleportation, which made it much easier than what you find in what was around before. Because with these wires, it's very easy to discover that there is something like quantum teleportation. It's very easy. I mean, it's very easy to discover this. While in the usual quantum language, it took 60 years for people to discover it. 60 years to discover this phenomenon. Let me look at the time. Yeah, okay, I just want to make a disclaimer here. It looks as if you can send the box from one side of the galaxy to the other side instantly. It doesn't really work like that. And that's not something I'm going to elaborate in today too much, because I've got other things to say. And of course, I can't stuff 150 pages in like half an hour. So that's, of course, impossible. So I can't tell the full story here. I'm just giving you sort of a glimpse of the story. But the thing is, like, that cap thing, it turns out that that cap thing here, you can't really do with certainty. It's a little bit like a lottery. You probably have heard about quantum uncertainty. You never know really with things happening quantum. And that's a bit true here. So that cap thing may not always be right. There may be some box happening, some weird error box happening, but then you can basically push the error box to the other side. You can just push it through the wire to the other side, and then BLAS can actually correct for the error. And that's really what happens in teleportation. Because I can still tell the story entirely with wires. It would take a little bit more time to actually clearly explain this all to you. But this just gives the idea how we can actually reason with these boxes and wires. And then, okay, then let me just go a bit fast forward. You can read about these things like in 2-3 months in all detail. But then to actually BLAS make the correction of Andrea, they actually have to call to each other. That's an important part. They have to call to each other. And this is quantum teleportation, really. So we explain this in great detail in the new book. You can find it also in the Dodo book if you want to. That's also explained in great detail. So that is really what quantum teleportation is. But it's something that's easy to understand with pictures and not so easy to understand in the usual quantum language. Okay, now I'm going. So this was like an old story from 2004, 2005. And around 2008, Ross Duncan and myself came up with something else, which is called ZX calculus. ZX calculus is now widely used in quantum industry. It's become a very important thing, and it's also widely used now in also teaching engineers and other people quantum. So ZX calculus is a refinement, a refinement of what I was just talking about, and it's based on something we call spiders. And it's really all you need. It's all you need to do your quantum stuff. And it's called spiders. I mean, I'm not going to go in details, but some students of me have proved recently that all the equations you can do in the usual quantum language, you can come up with spiders and with diagrams. So in 2008, we came up with the ZX calculus, and I'm going to now give an idea of what the basic idea is there. So basically, it's about making something that's a little bit more general than a wire, but essentially is kind of the same thing as a wire. So let me say, what does it mean to be a bit more general than a wire? Okay, so a wire has two ends. Every wire has two ends. So I can take my guitar cable here again. So my guitar cable has two ends. My guitar cable has two ends. Yeah, I mean, it's just one cable, but it has two ends, right? That's what it is. I'll show it again. Guitar cable has two ends. It's a long cable, but it has two ends. So wire has two ends, right? Okay. Now, what you do, if you connect two wires, then actually you get one wire. If you connect two wires, you get one wire. If you connect two ends, you get one end. If you have an extension lead for electricity, two extension leads, and you plug them together, you got one extension lead. I mean, it's longer, but you really got one extension lead if you plug them together. Now think, okay, I'm talking about extension leads. Some of these extension leads, of course, you can have an extension lead. I should have taken one here, which have multiple outcomes. You know, I should have one. I should be, okay. I don't know whether I can move this all the way there to, okay, you see this thing, yeah? This is you see my plug, I've got like many things coming out here. I've got many plugs coming out here. And so I can plug in multiple devices. So now think about a wire which doesn't have two ends, but more ends, like an extension lead. I mean, this extension lead is a good example of something like that. Yeah, so think about something where you've got more than two ends. And this is what we call a spider. Okay, a spider is a thing with more than 2 ends. Like a wire has 2 ends, a spider has a few more. So here we got a spider, but just like a wire, if you connect 2 spiders, you just get again a spider. Like if you connect 2 wires, you get again a wire. If you connect 2 spiders, you get again a wire. You have to do a little bit more counting, because if you take 2 wires and you connect them, you get a wire with again 2 ends. Now, if you get a spider here, this spider has 1, 2, 3, 4, 5 ends. This one has 1, 2, 3, 4 ends. Then, okay, we had 4 outputs, so that 4 outputs will stay. We have 3 inputs, 3 inputs will stay. So you have to do a little bit of counting here to make sure that no spider legs get lost in the process. You have to retain the spider leg. Well, the 2 ones which connect, they vanish. But the other ones just like poof together. They sort of fuse. We call this fuse. Spiders fuse together. Spiders fuse together. So that's all you need to know about a particular spider. They just fuse together. And if I've got a big spider network, you can call this a spider web. You can call this spider, if you got a big spider web like that, doesn't matter, just fuses together. And you'll see 1, 2, 3, 4 on the top, 1, 2, 3, 4 on the bottom, 1, 2, 3, 4 on top, 1, 2, 3, 4 on the bottom. So the spiders fuse together. Oh, wait. So this is an interesting one. So look what I've got here on top. I've got a spider with 2 inputs. I've got a spider with 2 outputs. Yeah. And if I make them fuse together, I get a spider, because there's 1 input here and 1 output. Then I get a spider with 1 input and 1 output. Do you remember this one? Do you remember this one? Let's go a little bit back. Oh, quite a bit back. It was exactly this one. This is the same. So of course, so this actually just shows, like, yanking my wire is just a special case of fusing my spider. It's just a special case. Yanking my wire is just a special case of fusing my spider. So once you talk about spiders, you can kind of forget about wires, because they're just part of the whole spider thing. It's just part of the whole spider thing. Just looking now. Yeah, okay. Right. Okay. So far we've been speaking about spiders of 1 color. So far we've been speaking of spiders, and you can actually already do a lot with spiders of 1 color. I mean, I'm not going to go in detail because I want to speak about quantum AI too today. I want to speak about quantum AI too today. So, like I said before, I'm rushing a little bit to this. If you read this in our book, it's much slower, of course, and the lectures will be much slower. But okay, now let's talk about spiders of different colors. So all you need are spiders of 2 colors. That's all you need, but you need 2 spiders of 2 colors. Now, let's think like in the animal kingdom, if spiders of different colors or ants of different colors meet each other, they usually don't like each other. They usually get into a fight with each other. So what happens here, you see there is a little bit of a tussle going on. There's a little, think of these 2 arms as one spider grabbing the other spider with their 2 arms. They're grabbing each other, and then their arms fall off. They pull each other's arms off. They pull each other's arms off. That's what happens when 2 spiders fight. They just pull each other's arms off. And then, okay, so they remain the same, but they kind of lost these legs. That's what happens when 2 spiders meet. That's what happens. Now, this is enough to now start to do some serious quantum computing. So now, from talking about these fighting spiders, we're going to go straight on to proper quantum computing as it's now done on quantum computers. So what you see here is a quantum computation. This is a quantum computation of some sort. It's a very simple one, but it's also just to show you, give you a very simple example. So what you see here, so look at the bottom, like at the first sort of horizontal wire. You see an horizontal wire which goes between a red spider and a green spider. And then when you go above, you see another horizontal wire now between a green spider and a red spider, and then an horizontal wire between a red spider and a green spider on top. So these things is the stuff you find in quantum computers. They're called quantum gates. They're called quantum gates. They've got a special name. They're called CNOT gates. But they're things you find inside quantum computers and which act on the quantum particles inside quantum computers. These things, so these things are the stuff you find in quantum computers. So what you see here is a quantum program. Just like you got quantum classical, like programs for classical computers, like all your apps and stuff like that, or MS Word or another program in your computer. This is like a quantum program, what you see here. It acts on quantum particles, it does things to quantum particles and changes them. This is a quantum program as you find now in most quantum computers. Now, quantum computers are still quite small. We're still trying to develop them, so they can't do very complicated quantum programs yet. They can only do simple quantum programs. So it's important to think now, how can we make this quantum program simpler? Can we simplify this quantum program in some way or another? And okay, what do we remember from spiders? Going back, two spiders of the same color, if they fuse each other, if they see each other, if they touch each other, they fuse together. See, they fuse together. That's one rule. Spiders of the same color fuse together. Spiders of different colors, if they touch each other with two arms fall off. Arms fall off. If they touch each other with two arms, two is actually important here. You see, we wrote it here, two wires. Two is important here. Okay. Oh, I see a bunch of green spiders connect together. Like these three green spiders, they're all connected together. And the two red spiders on the left are also connected together. They're connected together. So we can make them fuse. Look. So the two red ones fuse together and all the green ones fuse together. You see this? Showing it again. They all fuse together. They all fuse together. Boom. Right? Okay. Last time, one more time. They fuse together. Okay. What we see now, we see a red spider and a green spider holding each other with two arms. They hold each other with two arms. So these arms, they fall away. They fall away. You see the arms fall away. Arms go away. Arms go away. And now we have a much simpler quantum program. So you see, here we had three times we had to do sort of the vertical, the red-green spider gate connected by a vertical wire, horizontal wire. Here we only have to do it one time. So we just proved that doing it one time like this is the same as doing this three. This is a very simple example. This is a very simple example, but it's just showing that you can use these spiders to simplify quantum programs, and effectively, like people are using these spiders now to simplify quantum programs. This is so we are at Quantinuum, like Ross Duncan. I said I invented the spiders with Ross Duncan in 2000. Well, this way of dealing with spiders for quantum in 2007 and 2008, around 2007 and 2008. And so Ross Duncan is now the head of software in the same in Quantinuum, where I am. He's the head of software. He has a big team in Cambridge. He's effectively in Cambridge. He's not in Oxford like me. He's in Cambridge, and they built like software to make quantum computations possible and easy. And some of the things they do in their software is actually using the spiders to make quantum computations simple. And people also use at Google. There are people who use the spiders to make sure that if quantum computer makes mistakes, that you can correct them. So they use this quantum error correction. So Craig Guinea at Google and his team, they are actually using spiders to simplify, to make sure that quantum computers make no errors. And so there are other spiders are also being used by my friend Terry Rudolph, grandson of Schrödinger, to actually do computations and reason about computations and reason about errors for his quantum computer. He's also building a quantum computer. So the spiders are now being used a lot, like in many places in quantum companies. Like IBM is now writing a tutorial to quantum, also using spiders, but this is for engineers. They're writing a book for engineers, also using spiders. So you'll be hearing a lot of spiders stuff soon. And for example, in France, Quandela, they're now also using spiders for their computer. So these spiders are now used a lot in sort of quantum industry. And okay, so the kind of program I gave was kind of an easy program. It was a bit of a silly program because that program you can easily do on an ordinary computer. Like to make quantum computations more difficult, so programs on quantum computers, you need something else. You need phases. You need to think of these phases as decorations. You know, if you see a spider in nature, a lot of them have nice decorations on their back. Physicists call these decorations phases. So we just used phases of the moon. We just used phases of the moon to represent them. You can think of this. So you know, the moon has different phases, huh? And we used to represent them. Now, I mean, physicists would use angles to represent them, but you can as well use them as phases of the moon. You can actually choose whether you use angles or phases of the moon. Phases of the moon sort of stay loyal to the paradigm that we are not using numbers. We're not, so but it doesn't really matter. So the general spiders of quantum, they have phases, they have decorations, and when these spiders fuse, their decorations add up. Their decorations add up. Okay, so I'm going to stop here. I'm going to stop here. Yeah, I'm going to just skip the next slide. Okay, so I've said enough now. So there are 3 more chapters, but we can't give away too much. I mean, I didn't have time to say more, but I can't say more. Now, why can't I say more? Because we're doing this competition, remember, like high school students against Oxford University students. High school students are allowed to know about this stuff, but the Oxford University students are not allowed to know about this stuff. Otherwise, they could cheat. We don't want them to cheat and use this stuff. They have to use the stuff they get, like using von Neumann's quantum language. They have to do the exercise with von Neumann's quantum language, not with ours. So we can't put this in the public yet until we've done the experiment. So we have to be secret about it. So with what I've gave away, that's no problem. That's not too much. I didn't give too much away, and I can't give any more away. Anyway, okay, complete change of subject. Natural language processing and AI. So natural language processing, I already mentioned what that is. That's any way you interact with your computer with natural language. I'm now going to say, this is going to be more like I'm now going to more talk like a journalist in a newspaper. So there's an incredible progress with NLP and AI. You read this everywhere, all over the news. I mean, you experience it, the big progress with all the new AI things which is going on. Now, the reason this is happening, is because computers became so much powerful. And actually there's a lot to do with the gaming industry, because now all these powerful computers use the boxes which have been developed for the gaming industry mostly, and that created so much more power. There's of course also a huge increase in data, because all these companies like Google and Facebook, they're all stealing all our data, which means, and of course we are putting a lot of data outside on the internet, so there's so much data available everywhere. It's a factor 1 million in 25 years or something like that. And the combination of these two is what actually AI is using to do all the things it is doing. Importantly, it's not so much that there is a new kind of science. The development of AI now, it's not like there is a new kind of science going on, because the science goes actually kind of back to the 1870s, when people will start to think about what's called neural networks. And in the 1940s, people start to talk about neural networks as really something to use in computers. But it took a really long year, like 70 years before it actually started to, 60, 70 years before it started to be used a lot. So that's an important lesson. There is no real new science. It's new engineering, a lot of it, not new science. Now, there's a lot of shortcomings, which are also well known with the current AI, although they're very powerful. And this is now, I'm going to use some heavy jargon, but you can't interpret it, you can't verify it, it's not safe, it's not fair. I'm going to mainly talk about the last one. So there was a company, they don't like that you mention their names when something goes wrong, but there was a very big tech company, and they put out a chatbot a few years ago. They put out a chatbot, and the chatbot in 2 years became a genuine fascist. It started to become a racist. It started to insult people really badly, because they don't know what's happening inside. So this was a really big accident, because the company, and this is one of the biggest tech companies in the world, doesn't know what's happening inside. So we don't understand what's going on in this AI. That's why I'm calling it, it's not really scientific progress, because scientific progress is about understanding, and we don't understand what's going on. And this has a lot of other consequences. And it's also very expensive. I'm putting here a lot of things on, but like there is this thing, for example, that people may know, GPT-3, you can play around with. It costs 12 million in electricity alone to train it. 12 million in electricity alone to train it. So you can imagine what sort of carbon footprint, like how bad this is for the climate if everybody's going to start having one of those at home. I mean, it's just impossible, obviously. But so it's getting very expensive in many ways. And another thing which is I find a huge problem is that you can't really combine it with other computer science stuff. So the stuff which makes, okay, the stuff which helped us develop something like this, an iPhone, and all the computer science which helped us to get to a point in our society that we can actually build to that, all that stuff doesn't work at all, doesn't combine with AI. It doesn't combine, which is a big problem. So you now have these two separate entities. Anyway, historically, a situation like that actually kind of happened before. On the left, you see a picture of like the Babylonians. I don't think anybody in many history books of science, you will find a lot about Babylonian science. We are not using much of that today. But at the time, Babylonian science was considered as more important than the science the Greeks were doing. If you look now in a logic textbook, you still find the science of the Greeks. You don't find the science of the Babylonians. So this was a situation where and the Babylonians were doing things on the basis of data. They were doing things on the basis of data, while the Greeks were using like understanding and stuff like that. So the picture on the right is Ptolemy. Ptolemy was a physicist who for a very long time had a model of the universe in which the Earth was in the middle. The Earth was in the middle, and then all the rest was just going in some way around the Earth in some complicated way. And for a long time, this was the best model of the universe to use when you were in a ship and you wanted to navigate. Even when Newton's theory came out, his model was still better for navigation, because even relativity theory was built in his model, because it was statistical. Of course, that model is completely gone, and we still have Newton, and we still have all the other stuff now around, and we still all agree that the sun is in the middle and not the Earth, essentially. So these things happened in history before. Okay. Okay. I'm gonna basically, I think I'm gonna skip this. I'm gonna skip this in the benefit of time, So I'm now going to talk about our prehistory. So around 2008, there was like a few people at Oxford. I'm going to check my time. Okay, I'm okay. You know, 2008, there was 3 people at Oxford. Yeah, 2008 was a good year because we also had ZX calculus then. That was a good year. That was a productive year. Right. So in 2008 at Oxford, there were 3 people. This is Marnoush Sadrzadeh. She's now at University College London, a professor. At the time she was at Oxford, and she knew something which is called grammar algebra. You know the word grammar. Don't get annoyed by the word algebra. It's some kind of mathematics. It's some kind of mathematics that people use to understand when you say a sentence, that this sentence is well formed. So in English, a well-formed sentence would be, Alice loves Bob. That's a well-formed sentence. A badly formed sentence would be loves. No, it would be Alice Bob loves. Alice Bob loves is not considered as English. Alice Bob loves. But Alice loves Bob is considered as English. So there is some algebra which allows you to figure out what are well-formed sentences. And this is something Marnoush was working on. So I'm now putting on a picture. This is Jim Lambeck. So Jim Lambeck used to be a maths professor at McGill. He was a good friend of mine. He unfortunately died in 2012. But he's one of the people who pioneered grammar algebra. So who did like really important work, which people are now still using. And I mean, his first paper in this area appeared in 1956. It's called The Mathematics of Sentence Structure. So he basically is writing here about if you try to understand why, if you put certain grammatical types together, like verbs and noun, how can you understand that you put them together in the right way using mathematics? So that's what he came up there. And he didn't stop there. So look, like in 1999, he came actually up with a different kind of algebra, which he thought it was better to do the same thing. So these things are, this is a field which is still evolving, and he's been a really important person in that field, Lambek. Remember the name because the name is going to come back twice, Lambek. So grammar algebra, I know there are some scientists here, so let me try to quickly explain how that stuff works. Quickly, if you don't know algebra, then or a little bit of algebra, then just go get a coffee or a juice or something like that in the next 2-3 minutes. This may be obscure. So I'm going to use some symbols to give you an idea how this thing works. So if you, for example, have something like a noun, like Alice and Bob, which are nouns, then we're going to represent this by a symbol N. And then when you got a sentence like Alice loves Bob, then we're going to represent this by a simple S. So we got two symbols here, N for noun and S for a sentence. So not everything got its own symbol in language. Not everything got its own symbol. And that's kind of how this grammar algebra works. If you have something like a verb, like loves, in Alice loves Bob, then we're not going to give it its own symbol, because like loves in itself is not sort of a meaningful statement. You can't just say loves, you have to say who loves who. It's not sort of a meaningful statement, it's all right. Alice is kind of a meaningful statement, since you can ask like, who loves Bob? Alice. So Alice is a meaningful statement, which we use. It's called a noun or a noun phrase. So we got noun phrases and sentences, which are meaningful statements, but a verb on its own is not a meaningful statement. So what Lambek does, is says, okay, I'm going to represent the verb by, I put a sentence symbol in the middle and a noun symbol on the right and a noun symbol on the left, but I'm putting -1 to say that not that I have a noun, but that I need a noun. I want the noun. The -1 means I want one, not I have one. So basically what you do then, and that's where the algebra comes in, is you take this verb bit, so you got the sentence and the I want the noun on the left and I want the noun on the right, and then you stick a noun on the left and you stick a noun on the right. Like for people who know groups, this is like groups, but it's a bit weaker than a group. It's called a pre-group because it has left and right inverse not the same. That are just for those people who know groups. So it's called a pre-group. So basically, this is like you got the inverse to an animal, the inverse, and then when you stick those two, they cancel out. So now I want the noun, and here is a noun, they cancel out. So I ask the question, I get the answer, okay, we're done. So that's kind of how grammar algebra works. It looks a little bit like usual algebra you read it, you learn at school, but doesn't matter that you understand this. What is really important, and the message from this slide, is that I can represent this calculation as a picture. I can represent this calculation as a picture because I can take this n and this inverse n, or I want an n, and sort of let them cancel each other out with this cup-shaped thing. Because think of them as opposites. Think of them as opposites. So if you put them together, they cancel out. So like -1 and 1, they cancel out. Same here with these two. Sentence just goes through. So when we start with this, only the sentence comes through. So basically the whole message you have to remember is from this slide that grammar algebra or grammatical structure can be represented by pictures which use cup-shaped wires and straight wires, like we've seen before. You remember when I was talking about the picture, quantum pictures, we were using this sort of pictures too, the same pictures. And grammar algebra can be represented as the same pictures. That's the important. If you go to all this grammar algebra paper from I don't know, like from the previous century, you won't find pictures in there. I can tell you, you won't find them. They will always be these symbols, but you can if you want to. That's the important lesson here. Okay, so I taught you something about grammar algebra, and the important lesson to remember here is that grammar algebra can be represented as pictures, the algebra, or the algebra in general. This is not about or grammar in general. So grammar can be represented as picture. So also at Oxford then, I mean, I brought Steve Clark up before because he's now also working in my team in Quantinuum on the same things. Then he was a faculty in Oxford. So we started thinking about something else, which is called vector space NLP. The only thing you have to remember here is that that's what's now being used in all modern NLP, in all the big language models like GPT-3. They represent the meanings of words. Meanings of words is what you find in a dictionary when you look up a word. So they represent them what's called vectors. And importantly, vectors is what's also used in von Neumann's quantum language. Vectors are also used in von Neumann's quantum language, but they now also use vectors to represent the meaning of a word, rather than sort of a description that you find in the dictionary. So Steve was like working on that sort of stuff. And I mean, what was I doing? I mean, I spent an hour talking about what I was doing. I was inventing pictures for quantum. That's what I was doing. I mean, which looks very much unrelated to the two things above. Two things above, okay, grammar and meaning, you would expect them to be closely related, grammar and meaning. But yeah, mathematically, they were very different. Like one was this algebra, the other one were vectors, and they looked very different. And okay, I'm showing the book again, and then the question Steve asked the question, because many people had asked him before him, and Steve asked, he said, how can we combine grammar and meaning? You know, if I tell you a sentence which you never hear before, when I tell you a sentence you never hear it before, but you understand, you know the meaning of the words of the sentence I'm saying, you know the meaning of each word, then you know what I'm saying, if my sentence is correctly formed. Let me say a sentence you probably never heard before. Here in Bob's guitar studio, Bob is giving a seminar on quantum pictures and on quantum natural language processing. I'm sure you never hear that sentence before in your life, right? You never hear that sentence before in your life, I'm very sure. But you understand it. You understand it. How do you do that? How did you combine the meanings of the words together with the well-formedness of the sentence to actually understand what I'm saying here? So we know how to do that. We know how to do that. But can we actually teach a machine how to do that? That's the question. Can we teach a machine that understands meaning of words and understands grammatical structure, like as in the grammar algebra, to actually understand the meaning of a whole sentence using these ingredients? So that's what we were trying to solve. Okay. Okay, now we go to Montreal, 2004, long time ago. We're at McGill, Montreal, and I just had written these first papers on quantum teleportation in pictures. I was very, very eager to give seminars about that. So I was giving a seminar in Montreal, and I was talking about teleportation, which I sort of explained before, in McGill, in the mathematics department. And in the audience was Lambek. I mentioned Lambek as he came up in the 50s with this grammar algebra and all that. So he was in the audience because he was based in Montreal. And then when he saw me talk about this, he saw me talk about quantum teleportation, he screamed, "Bob, this is grammar." He told me, "Bob, you're talking about grammar." I said, "No, I'm talking about quantum teleportation." I said, "No, you're talking about grammar." Okay. I mean, I didn't know anything about grammar algebra at the time. I didn't know anything about it. So of course, I didn't know whether he was right and wrong when I said it. I know now that he was 100% right. He was exactly right. He immediately recognized that grammar takes the same form as my pictures I was using for quantum teleportation. Now, okay, let's put a few things together here. In von Neumann's language for quantum, you represent systems, quantum systems, or how they are, states of quantum systems, by vectors. In modern natural language processing, so how we interact with language with computers, we represent meanings of words by vectors. Now, if you want to start thinking about how quantum systems interact with each other, also how these different vectors, if you want to interact with each other, then we know you use the quantum picture language, because that was Schrödinger's sort of idea about what's important about quantum, and therefore we developed the quantum picture language about how quantum systems interact. And we have to think about how words in a sentence interact with each other, play along. Well, that's grammar. Grammar tells you how the words play along with each other. And as Jim Lambeck said, grammar can be written down in the same picture language as we use for internet quantum systems. So we got a perfect mapping here from meanings of quantum particles, or what quantum particles are and how they interact, to what words are and what meanings of words are and how they interact. They obey the same mathematics. They obey the same mathematics. So to bring meaning and grammar together, we can just use the pictorial quantum formalism. We can just use it. We can use that. And that's what we did in this paper, which the first version was in 2008 again. So this is a longer version in 2010. So we basically said, okay, we have this new theory which explains how meanings of words and grammar interact and tell you what the meaning of the whole sentence is. Like the long sentence I said before, which you never heard before. So we came up with that. And this is generally a new theory. This is a new theory within AI, you could say. This is a new theory in AI, and it did something very special. It combined like these meanings represented as vectors. I was talking about meanings of word represented vectors. It's what's called, you can use machine learning. You can use machine learning to learn them. On the other hand, the grammar is something that's very theoretical. So this also was like something that combines new AI with traditional computer science. So we're starting to get the best of both worlds in a hybrid. And it was probably one of the first things which did this. Anyway, so we had this new theory. I can explain how it kind of works. And then I'm almost there. So this is a picture. It looks very much like a teleportation pictures, but really what it is like you have these three boxes, and you have to think about this as the meaning of the word Alice, the meaning of the word hates, and the meaning of the word Bob. So these are the meanings of words. Like I showed before, a picture like that corresponds to grammar. And you see, by putting those two together here, the meaning and the grammar, we get one expression. We get one expression which combines the meaning of the grammar, and then this actually we think of as the meaning of the sentence as a whole. And then we did a lot of experiments with that, and it worked. The theory worked. We did a lot of experiments, and the theory worked. I'm going to skip this, and then of course we got a lot of feedback about it, and people start to call us quantum linguists. So like in New Scientist, they called us quantum linguists. But at the time, we didn't care about quantum implement. We were trying to solve a problem which was nothing to do with quantum, like combined grammar and meaning. Why's quantum there? Well, the solution came from the new quantum picture formalism, but a priori that had nothing to do with quantum. Okay, let me skip this. I'm going to skip this too. This is not so important. So I'm now just going a bit quick because I'm running out of time. Okay, I'm going to skip a little bit. There. Right, so we had this new formalism for quantum, which we used to combine grammar and meaning. And for a long time, we were trying to sort of just use this on ordinary computers. Well, not me, like Steve was doing that and Mernush was doing that. They were putting this on ordinary computers. I mean, I don't know how to do that sort of stuff because this is like a special skill set you need. But they found it difficult. They found it very difficult to do that because very quickly the computations took too long, or you couldn't store your states in memories. Computers couldn't really deal with that. Now, that wasn't entirely a surprise because we were using a quantum model. We were using a quantum model on an ordinary computer. And a long time ago, Feynman had said, if you're going to use a quantum model for anything, for example, for chemistry or for physics or whatever, then you should use something which we call a quantum computer now, and which now exists. Of course, they didn't exist in 1980s when Feynman said that, but they now exist. They didn't exist really, they didn't really exist in 2008 and 2010 when we came up with our new theory, but they now exist. They do exist. And I mean, for a while, yeah, okay, no, let me just continue. So what happened is, like, in the first paper we wrote, then that's Will Zheng and I. Will Zheng is now the head of quantum at Goldman Sachs. So banks start to have like quantum teams now. So Will Zheng is the head of at Goldman Sachs. He did his PhD with me at the time. And in 2016, we start to look in the possibility whether quantum algorithms, which is very much the reason quantum computing exists, could be used to do something with natural language, and to do something much faster than we could do on an ordinary computer. And we figured out, oh yeah, these things exist. You can use like quantum algorithms and all that to do natural language processing and do it actually much better. At the time, there was no way that with what we proposed that this could ever be done on any quantum computer that even exists today. We were sort of we were talking about very idealized quantum computers. Skip this. More recently, and that's actually when we start to work with then called Cambridge Quantum Continuum, Konstantinos and Giovanni and Alexis and I, and also Stefano, in fact, who worked on that too. We figured out how we could actually do something with natural language on the quantum computers that are now available. I mean, then available in 2020. We figured that out. Again, I'm just gonna, you don't have to understand these pictures, but you see, this is a picture, the dots you see here are spiders, your spiders. And what we start, basically some of the things we did was like just playing around with spiders, like you see here. I'm sort of unfolding spiders and things like that. This is all just spider reasoning to turn a language diagram into a quantum circuit. So this is actually a quantum circuit. So we were able to turn natural language in quantum circuits. And then, I mean, we did some, this I'm not going to elaborate on this, the way we actually did this. Then we actually did it. So we actually were able to do natural language processing on quantum computer. Basically, we taught the quantum computer some stuff. Then we asked a question and we got an answer, and the quantum computer gave the right answers. So we were starting to do natural language processing on a quantum computer. And we did it bigger, and we're still pushing, and we're still making it bigger and bigger, because also the quantum computers are getting bigger. So that's sort of stuff that we're doing now. That's going on today. And what is also going on today is that you can do the same now. You can do exactly what we were doing in the two previous papers, because all our software, which we produced for this, all the tools which we produced for us to do it, we actually made publicly available. So they're just out there. You can take them, you can use them. We've got a Discord channel where we help you if you want to become part. We've got already 250 people there, or 300, who are now actually using all this stuff just to play around with it. So you can do that too. You just write me, and then I can send you an invite for the Discord, or you write anybody else from our team, and you can get an invite. But so basically, we made all our tools available. First, we just made them available. And now, more recently, last week, we actually made them available in a way which is much easier to use too. It's much easier to use now. You don't have to be a programmer anymore to use it. And we're going to make it even easier in the future. So this is going to become easier and easier and more richer and richer. But so you can all now use our tools that we developed to start playing around with quantum natural language processing in the way I explained. I think I'm going to go to the end, because I'm really getting very late, and I want to leave some time for questions. So here are the documents. You can find the technical paper about this. The GitHub is here. I'm happy. So this can all be shared in the chat here, but it's all, you can just Google for Lambek. Oh, by the way, you know where the name Lambek comes from, of course, now, but it's with a Q at the end. So this is not an existing word in any language, L-A-M-B-E-Q. So it's very easy to Google it. It's very easy to Google it. Okay, gonna skip this. Okay, the last thing I want to say is, one fun thing we did with Lambek is we start to compose music with it, and we in collaboration with Eduardo Miranda, who's a composer, he's a composer and also a professor of computer music. We actually started to use Lambek to actually do something with music and stuff like that. And then a little bit of, I've been trying to be a musician like my whole life, and the kind of slide, I'm sitting here in a music studio, by the way. I mean, I can even show it on my, so you see this is a music studio. I don't know whether you can see this. I'm showing you around, this is a music studio. So you see drums and guitars and things like that. Anyway, so I've been trying to be a musician my whole life. And then after we did this thing with Lambek, which we actually called Quanthoven, we gave it the name, the use of Lambek for music, we actually became first in the classical charts with something we had produced with the help of a quantum computer. So that was the song there, Bob Cigar Bus, is something we produced using a quantum computer, and we converted in classical charts. Okay, I'm ending here. Thank you.
Thank you, Prof. Coecke, for the very interesting talk. So it's now for Q&A. There are already 2 questions at least in the chat box. Should we try to read them, or you want to ask the question then, yourself? Not sure whether the person is still here. One question is from Thomas Clark. If moving the boxes around doesn't matter, does that suggest some type of commutation or stroke associativity relationship?
Okay, that's a good question. So I mentioned the word categories here in the very beginning when I was talking about saying we actually formulated things in a complicated language rather than pictures initially. And so that language is the language of monoidal categories. And then you got like properties there like associativity and commutativity. Typically people call it symmetry. There's lots of properties in this algebraic category theoretic terms which basically correspond to the moving the boxes around, and like it's a bit more than associativity and commutativity. There is also something which complicatedly called bifunctoriality. So it's much harder to, these are not easy things to study. This mathematics, the symbolic mathematics which corresponds to the pictures, is not easy to study. Like category theory for a long time was considered a postgraduate subject, not something you would ever teach like in a undergraduate curriculum, although it's now happening. It was considered as a postgraduate topic. And in particular, the type of category theory which corresponds to these pictures is even within category theory considered as complicated. So, but yes, you can actually translate all this moving around into usual algebra with things like commutativity, associativity, but you need a lot more than that. You need a lot more than that.
Another question is from Jan Blommaert, I hope.
Jan Blommaert, I mean, this sounds like a Flemish name or a Dutch name, so I can pronounce this easily. Jan Blommaert.
Where should I start for learning more about your picture language before the book is published?
Okay. So, I mean, the book's going to be published in 2-3 months. So the book is, of course, already available. The book is, of course, already available. And it depends what your background is. If you got like, say, I would say, if you know basic linear algebra, because you're an engineer or you remember it from university when you studied physics or maths or something like that, then that should be enough. That should definitely be enough to actually read the Dodo book. So it depends on your background. It depends on your background. Let me think, are there other things? Yeah, I mean, there is just a need for this new book. So we just wrote it, and there's really nothing else around, I would say, at this point, until 2 months. If you don't have a minimal linear algebra background. Because Dodo book, you need, well, actually, you can get quite far in the Dodo book without linear algebra, to be honest. You can get quite far. You can get to teleportation without linear algebra even. So yeah, even there you can get quite far, I would say.
Right. There are more questions from the chat box. Clarissa, do you want to ask yourself the question? You can unmute, I think.
Okay. My question is just basically, what do you see the future? Well, what impact of the development of Lambda on the future of quantum AI and AI in general?
Okay, that's a very good question. So I mean, I couldn't elaborate too much on that here, but in the beginning, when I was talking about current AI, I talked about the fact that we don't understand it, that it's not interpretable. Another term people use is it's a black box. So a lot of AI currently is a black box. We don't understand it, and we consider Lambda just as the way it is now, just as one step to open the box, to better understand what is inside. In the way we have implemented, implementing language on a quantum computer, you can actually see different parts of language. You can see the different words and how they sit together. This would not be the case in any modern natural language processing like neural network. But this is only the start, because natural language is only one way of interacting with each other, of perceiving stuff or imagining stuff. Language is only one. And by the way, if I tell you something, when I was talking about my music studio and that I'm giving a talk here, I'm sure you didn't see like a white page in your head with words written on it. What you saw is probably some image of me sitting here between musical instruments and stuff. So you imagine something which you associate with the language. And we are now building models which actually go beyond language, and which go actually start to actually represent much more of our cognitive features and our way of interacting with the world, also like the physical space around me and all that, in a much more bigger integrated model. So this is so far down the line, we want to come up with a new model for reasoning and AI, which is actually not a black box anymore, that we actually understand. And this also makes it more safer, will also make it more powerful, and will also make it more human-like, like you and I. So that's one thing we're trying to do on the front of making it really much broader AI than NLP. And then another thing which I also didn't have time to talk about is we got an entirely new model, an entirely new sort of grammar algebra, which is not anymore just about sentences, but which is about entire texts. It's about the meaning of big entire text, so that we can actually compose meanings of sentences to get text. And that's something we're also now implementing. And that's something nobody has ever worked with, really. So it's an entirely new theory of language, really, of natural language and natural language understanding. And so that's something which is now also start to become integrated in Lambda. And we expect that there we can actually do things that you really can't do with most modern, with a lot of modern natural language processing tools. So those are two directions, specifically on the front of natural language, and then more broader AI. And by the way, the new model of language actually, it's very interesting because we all speak different languages. So the typical grammar algebra, you would actually have to come up with different sort of systems for different languages. Our new language theory is independent of the language you speak. So we've got a way to go to a meaning via structure which doesn't depend on the language you speak at all. At the moment, most natural language processing only exists for English because of the dependency on grammatical structure. And there are not many grammatical tools around in any other language than English, unfortunately. And so hopefully with our tools, it's going to be much more inclusive for different languages too.
Okay. There are more questions pouring in. I hope the committee allows the Q&A session to be slightly longer. There's a question from Thomas Clark. Is he here? You could unmute yourself and ask the question.
Okay, thank you. My throat's a bit dry. So the question I had is so quantum systems, we know they scale the dimensionality scales as 2 to the n at least for qubits, and no one else is using qubits. And that higher dimensionality in the context of natural language processing, would that allow you to represent perhaps if for a finite number of qubits versus a finite number of bits, even if the number of bits is quite a bit larger, you could represent more complex words? Just
exactly. It's not just about complex words. The dimensionality of words isn't really that much of a problem. The problem we were dealing with was the dimensionality when you start combining words, because the way they combine is basically exponentially blowing up itself because of the tensor structures used. So that was the reason. That what you're talking about is really the reason we had trouble doing anything with this sort of interactive model of language on a classical computer. And the first reason to go to a quantum computer is because that exponential blow up just vanishes. So indeed, you can represent. So the sort of, I mean, an interesting thing is like in a lot of the quantum advantage stuff, if you know anything about what's been going on, like the stuff which Google did at some point, and which also happened in China, in Zhang Wei Pan's group, a lot of that has to do with that the state which you produce and do something with simply doesn't fit on classical hardware. It becomes too big. And that's totally what you're sort of saying. So complex interactive meanings, maybe not single word meanings, but complex interactive meanings like meaning of sentences and meanings of text, there's no way you can put them on classical hardware. And that's where quantum hardware gives you an advantage, even if it has much less qubits than classical hardware because of the exponential blow up. So you're very right. The answer is yes.
Okay, thank you.
Okay, the next question is from Reza Zainuddin. You want to unmute yourself?
Hello, can you hear me?
Yeah.
Okay.
Okay, thank you, Prof. Hello, Professor. I'm just very curious as to whether or not your ZX calculus that you stated previously is a suitable replacement for category theory, as it seems that you're using it as a replacement. At least that's what I can see from.
Yeah, I mean, the way to say it's the way to say it, like ZX calculus can be thought of as category theory, not even a replacement, but as category theory. So what you've got is like this equivalence to represent category theory either symbolically or to represent it diagrammatically. Now, the diagrammatic representation is so much easier than the symbolic representation. So I haven't been using symbolic category theory for, can't remember, 10 years, because it's so much easier to work with the diagrams. It's an alternative. Now, some people who are actually building software about ZX calculus, they actually have to go back to the category theory, because that's just how software works. So in that way, you still need a category theory. Also, if you're using ZX calculus for quantum computing, you really need no category theory at all. If you're going to think about ZX calculus as a theory of physics, and thinking about different models, then you probably need to go back to category theory again. So, but as far as quantum computing is concerned, and you know, an historic bit is like it took a really long time before ZX calculus got popular. It took a really long time. It actually almost needed quantum industry to start. Part of the reason is, and that's connected to my first remark about the first paper of 2004. When we published ZX calculus, we published it as category theory, because otherwise nobody would have taken it serious in the sort of communities we were trying to sell it to. But then we had to actually tell people, and that took a very long time, but you don't have to know category theory. No, it's not necessary. It took like 10 years to convince people that they didn't have to know category theory to work with ZX calculus. Now that's achieved. Finally. And like I said, like, when our books comes out, and soon there will also a book by IBM on quantum for engineers, that will be full of ZX calculus. And I think then the point will be made that you don't need to know anything about category theory to actually do ZX calculus.
I see. Thank you so much, Professor, for answering my question.
Right. The next one is from Sheila Ditya. Is she here? Or?
Yes. Hi,
He.
Professor Bob Coecke. Can you hear me?
Yes.
Yes. So I'm Siladipto. My question is, as you told that every interaction and every operation, what we can do in quantum theory can be represented in terms of moving boxes and wires. And if this is yes, and the next thing related question is in this framework, is there any new prediction in category theoretic treatment of quantum theory, which is different from quantum or standard quantum theory?
Okay, so those are two questions. On the first question, so there are two. Let's just talk about qubits to keep things simple. So like the two-dimensional particles you use typically to do quantum computing. So there are two theorems. One is that the ZX calculus language of wires and boxes, or spiders, of wires and spiders, is universal. You can express any quantum operation in ZX calculus. That's theorem number one. Theorem number two is you can prove any equation between quantum processes, so between then quantum operations, and formulate as ZX diagrams by using, exactly like you're saying, moving boxes around and things like that. So yes, all equations in quantum for qubits can be done with ZX, and especially Kwang Long Wang, who's working with me, he has generalized most of that to all other dimensions too, and is now even working on infinite dimensional stuff. So to do exactly the same thing. So the answer to your first question is yes. The answer to the second question, are you going to discover something new? Well, I mean, we definitely are not going to discover something that you couldn't discover I mean, couldn't as in the sense that it would be different in von Neumann's language, because the languages are pretty much equivalent. That's the statement that whatever you can prove in one, you can prove in the other. However, you may want to think of something like a ZX calculus or a diagram language as something that is not tied anymore to the traditional Hilbert language by sort of generalizing it. And then you can start, and we are also involved in a project with people like Carlo Rovelli, which is then moving more towards quantum gravity, and to see whether suitable weakenings of this calculus, which was specifically, which of course captures all of quantum, but that suitable weakenings may take you to sort of a more interesting theory, which like combines gravity and quantum, so to say. An interesting part, which I didn't talk about here, but which is actually also in our forthcoming book, is that a lot of aspects of relativity theory can also be captured by the same diagrams, like the aspect that you can't signal faster than light and things like that. They can be captured by the same diagrams. And there is quite a large community now working using this sort of diagrams and things like that to start thinking about what's called indefinite causal structure. That's where you got superpositions of space-times. And that's really what you would expect to happen in quantum gravity regime. So this sort of language can also be used towards, like I said, we're in a big project. We just finished 3 years of it. I'll actually be given a new public lecture in June, another public lecture in June in the context of that quantum gravity project, which also will be publicized.
Okay, thank you very much.
I think the next one from the Groudance is probably on something related to what you have said.
Yeah.
Yeah, I think you just answered my question. I was just curious whether there are any implications for the structure of space-time from the pictorial view of quantum theory.
So yes, I mean, I can elaborate a little bit with it. So as we said, like the Penrose started like using this sort of pictures specifically for space-time. Now they kind of are used in a somewhat different way now than sort of what Penrose intended. Penrose was basically using them to describe the algebra we used to describe space-time, while now we are using them to describe the processes which takes place in space-time, which is different. So Penrose's use in the context of space-time of these pictures was different than the modern use of these picture in context of space-time, which are much closer like the way we use them in quantum. But I mean, it's not hard to see the connection between things like ZX calculus when you see ZX pictures and the sort of diagrams which sometimes show up in work like loop quantum gravity and so, I mean, not exactly in the same way, but people already have been working on specifically, there are papers around which trying to connect loop quantum gravity to ZX-like diagrams. They already exist. So yes, there's work going on there. And personally, I particularly like the incarnation, which I didn't talk about here, of the sort of no signaling idea, the no faster of light signaling in terms of boxes. It's really simple. It's super simple. It's the simplest diagram you will ever see. I mean, you can read about this in the Dodo book and also the forthcoming book. We use that.
Thank you very much.
Right. Any more questions from the audience?
Can I ask one question?
Ahmad?
Hi, Prof. I'm just curious, want to know about what is the difference between the Lambek grammar calculus compared to Chomsky, I think?
Oh, okay, good question. So they're kind of, so I mean, Chomsky did a lot of stuff, but like let me emphasize on two things. You got sort of generative grammars which Chomsky produces, and basically those grammars are telling you how to build. They give you little building blocks for how to build a grammatically correct sentence. So you can actually then build a machine who starts to produce grammatic. There's no, okay, correct grammar, correct grammatical structure. You can build a machine which starts producing it. The algebras, the Lambek stuff, the algebras, they are a bit different. They tell you that given a sentence, how can I know that it's correct? So one is actually basically given a sentence, how do I know? The other one is how do you build a correct sentence? The Chomsky stuff. But we're actually now working. I mean, we actually have. I mean, we have reached a better understanding on how the two are connected now. And an interesting thing is to connect the two. You actually have to go to diagrammatic language. It's very hard to connect them in symbolic language. So in a forthcoming paper, we will actually connect the two. And but by the way, all what I'm talking about today can also be done with the sort of Chomsky-like grammars. I mean, it's not in anything we've published yet. It's in a paper we probably publish within the month. But so it doesn't really. So there is a fundamental difference. One is like about generating. The other one is about verifying. But you can connect the two. You can connect the two if you use the right mathematics.
Thank you.
Okay. Any more questions?
Can I ask a question? Thank you, Professor Bob, for interesting talk. So my question is, what is the difference between the classical structure that you described by the spiders and quantum structure?
Okay, a bit louder, please. I can't hear it very well.
What is the difference between classical structure that you described by the spiders and quantum structure? Can you hear?
Oh, okay. That's also a good question. Like, so of course, if you use, I mean, at some point I say, okay, this is quantum computing, but you can also with the C0 gates, but you can also think about this as a classical computing. So of course, as a computation, to get a proper quantum computing that you can't simulate classically, like directly, you need these phases, you need these decorations on the spiders. They basically is what you need. And then there are some conditions on it. They shouldn't be stabilizer. There's some conditions on it to make it truly quantum in a sense that it can't be classically simulated. Now, in a different way to answer that question is sometimes you may draw a diagram where you got both quantum and classical working together. Like, for example, in teleportation, you use quantum particles, but then you also have classical communication, a classical phone. And then the way we represent this, which I didn't talk about this today, but which you find in the Dodo book and you'll find in the new book, is that it's a simple trick which we use to distinguish classical from quantum. If you want to have both in the same picture, then you actually have to double your quantum pictures. You have to draw them twice. And then basically going from two pictures, from the double quantum pictures to the single classical picture using a spider, that's the same as a measurement. So you'll use the spiders, a spider with 2 input legs and 1 output leg, as a sort of transition from quantum to classical. In a way, this was already, for those people who know density matrices, this sort of trick was already baked in the way we use density matrices, as invented by von Neumann again. It was already kind of baked in the von Neumann quantum formalism, that you go from 2 to 1. But it's of course graphically a very nice trick.
So as a follow-up, so actually, when you have these 2 spiders described by red and green, so when they interact, it can form a group, right? So from the groups, you can have a process to a quantum structure, and it's like a representation. Is it really a representation?
So I mean, there's quite a lot of good, even if you have 1 color spider, just for the reason of the algebraic structure that's sort of behind it, you already get a group. And you don't have to, just from the structure of how the spiders work, you get a group which we call the phase group, So a theorem which you can show is that if you got the red and the green spiders, that I mean, there's actually 2 groups going on. There's the phase group, and then there is the group of what we call classical points of the spider, which are the copyables, and one is a subgroup of the other. Now, if you got 2 pairs of spiders and they interact as a bialgebra, so ZX calculus, I didn't talk about it today, as another equation, and this makes it actually that the red and the green spiders form a bialgebra, and in the space of qubits, actually a Hopf algebra with trivial antipode. So you can basically then, you can basically start doing quantum algebra representation theory with these things. So it may be interesting to know that Jean Magid, who's one of the biggest people in quantum groups and all that, is now working on ZX calculus and looking at this from this sort of perspective, as you were mentioning. So that's finally the quantum group people are looking at ZX calculus, which is a very good thing. And somebody else, a PhD student of ours, Alex Couten, is working on precisely the sort of questions you are asking.
So actually, there is a process from classical to quantum structure.
Well, the process from classical to quantum structure is just, I mean, it's an embedding. It's an embedding, and it's a spider from 1 to 2.
Okay, thank you.
I think probably we have to finish soon. But before we go, perhaps I have a question myself.
That's fine.
The first time when I got into your sort of diagrammatic kind of calculus thing, one of the things that sort of worries me is the proliferation of the diagram into complicated stuff. But then you get your spiders to help you. So in graph theory, for example, they normally use some kind of filter, like removing all the nodes which are not so important. But in your case, it's probably something different. So
I mean, it's a good question. So a few people, I think these has mainly be like teams in Nancy and also some people in Oxford, and they have been developing things which is called scalable ZX calculus. So it's basically a meta theory on top of the diagrammatic theory to simplify your diagram, because in practice, a lot of stuff will be repeated. There will be a lot of repetition and things like that. And so people have been developing calculi on top of the calculus to actually sort of compress very big stuff into small stuff and then still be able to do the same intuitive calculation on the much smaller representations. Now, so that's one side of the story. Of course, the other side of the story is if your ZX diagram becomes very, very big, then just think about doing this with pen on paper in Hilbert space. Then it's then when it becomes totally important. And so it is important to develop, computer tools to actually deal with rewriting and all that, because, and actually that you can actually just focus on parts and things like that. I mean, there was a kind of software available, which was Quantomatic, but it's kind of retired now because it wasn't fit for purpose anymore. And people are now starting to develop new kind of software to do exactly that. There is, for example, the PYZX, which does automatic rewriting, in particular for sort of simplifying quantum circuits using ZX. So that's already available, PyZX. And people are now developing more rewriting tools because it's not always obvious to do it with pen and paper. You're totally right. And we've got computers, so why not use them to make stuff much easier? I mean, you can still look up Quantomatic. So Quantomatic is just out there, but it's kind of retired. Nobody's working on it anymore.
Right, I think with that, probably, so before we go, I think the committee would like to do a group photo. Somebody could have?
Yes.
So all participants are encouraged to open up their camera.
Okay, ready everyone? Okay, ready? 1, 2, 3. Okay, one more. Ready? 1, 2, 3. Okay, one more. Ready? 1, 2, 3. Okay, thank you.
So I guess that's it. So let's just give our thanks to Professor Bob Coecke, who has delivered a very interesting talk.